titration. Section 10. All right. This is called potentiometric titration. When we have in a redox equation, in a titration redox, we call it potentiometric titration. It's a volumetric method in which the potential between two electrodes is measured. Reference and reaction indicator electrodes as a function of an added reagent or a titrant. The part of the curve that has the maximum change marks the equivalence point of the titration. So we have two electrodes, okay, and we have a reference and an indicator electrode as well, and we have a titrant that's coming from the burette. And we will do this titration until we reach an equivalence point of the titration. And there at the equivalence point, there's a maximum change taking place in the potential. يعني بنكون potential and then suddenly we become a much higher potential. Pretty much like as well titration curves in a pH. For reasons of practical difficulties, we usually do not use the hydrogen reference electrode as because it has a zero potential. However, for this course, we're going to assume that our reference electrode is zero, and it's the hydrogen electrode. بس أنا حفرجيكم what it is for sure. Typically, when I want to use a potentiometric titration, my reference electrode is the standard chamomile electrode, SCE, and the potential of SCE is 0.245. We follow the variation of the EMF of the cell to the volume of the titrant added. So we're looking at the E of the cell as a function of volume. So here we have a cell, as you can see, we have an oxidation half, reduction half. And in this case, we're going to titrate titrant with a burette on only one side of the cell, okay? And we're putting it on the reduction side, cathode, positive electrode. And it has a concentration C2V2. The analyte of this side is some analyte is C1 with a concentration C1 with a volume V1. We call this part killa, where I have the analyte and the titrant, the indicator half reaction, okay? We call it the indicator half reaction. And overall, okay, we will see as the indicator reaction, because it's a single cell, guys, where I have a reductant and the oxidants added to a single cell, E of the ox will equal E of the red when at some point, يعني هيدا E ox will equal to E red, and we're going to call it E of the solution. At equilibrium, these will equal to each other, the reduction and the oxidation, but the overall, somehow there's an E of the solution. But to get a voltage, we have to compare the E of this side to an E of a reference half reaction. Now, for this course, if I consider that the E of the reference reaction is the She hydrogen electrode, that means E reference equals 0. So E of the solution is some number, E reference is 0, and we know that the overall potential, delta E, will be E cathode minus E at the anode, and so E cathode minus E anode, يعني it's the E of the mix at equilibrium minus E of the reference. Typically عم نقول E of the reference بهي الحالة 0. That means خلص ال E of the cell is simply the E of the mixture at equilibrium, or E of the solution at equilibrium. Okay? The truth of the matter, we can never do potentiometric titration with the reference being the She electrode. We have to use the standard chamomile electrode, which has a minus 0.254, just أكد, 254 potential, 245, okay. 245 potential. So the truth should be that this E of the reference should be the standard chamomile electrode, which has a minus 0.245 reduction potential. And so whatever the E of the mix, I must minus a minus, add to him a 0.245, and the overall curve simply goes up this value point. But for this course, always we're assuming it's the She electrode that is the standard, okay? Now on this end, if we take, for example, this side, the anode side, the analyte, and we add the titrant and the anode side of the cell, and we put the standard chamomile electrode on the cathode side. First, these two, the titrant and the analyte, reach some E of the mixture or E of the solution at equilibrium, where the E ox, in other words, E of the titrant, equals للE للanalyte. Red. يعني لأن هون it's a single value. But this ox red is not this overall cell ox red. So we get this part is E of the solution. And we're comparing it to the E of the standard chamomile electrode. In this case, what do we have? The overall E will be cathode minus anode, the E of the standard chamomile electrode minus the E of the solution. Okay. And again, if this was a She electrode, then it would be 0. If it's the standard chamomile electrode, it's a minus 0.25445. Or if it's a She, it's a 0. So E overall will be minus E of the solution if this is on the anode side. For this course, okay, only, I needed to talk about those, but for this course, شو بيقوموا بيعملوا? They mix everything in a one pot. يعني it's not really a cell. They put the analyte in a container. They add the reference electrode in that same container, not in a separate. And they, so this is the analyte. And they add the titrant, oxidant or reductant, in the same container. So everything is in the same container. Okay. So we don't have, E cathode, E anode. We have E of a solution, which is the mixture of whatever my analyte is with my, plate of the analyte with a titrant. And this becomes E of the solution, and we do E of reference, and we make sure that the reference is the standard hydrogen electrode, always on the cathode. I want you to assume that it's always actually on the anode side, and therefore the E, when we're doing a titration, is simply E of the solution, regardless of if it's on the cathode, anode side, and we're always assuming it's with the She electrode. So here we're doing a direct contact indicator electrode, and we simply take whatever the E of the indicator electrode as the E of the overall titration taking place. Now here in this next piece, we're going to see some, it's not confusing, it's very simple, بس الفرنش كتير بيحبوا هون الانز والالفا والجاما when numbers suffice it. Okay. We have an overall reaction, and if we split it into two half reactions, so the red here goes to ox, red 1 goes to ox 1, and ox 2 goes to red 2, okay? And this is what I'm assuming here. And here, this is plus n prime, so number of electrons مسمينا n prime, وهون plus n, number of electrons for this part مسمينا n. Okay, so this is the two half reactions, but not written as reductions. If I have, even though this is undergoing oxidation, I must write it in the form of ox1 plus n prime, red 1, in the form of reduction. Okay, so these are the two reactions, half reactions for the overall equation written in the reduction half. And I'm going to solve the reduction potential of each. E1 will be E naught ox red 1, 1 plus 0.0592 N prime, which is the number of electron transferred for this half reaction, log ox على red, because there's a plus sign. On the other side, other half reaction, E2 reduction potential is E naught of the 2 ox red plus 0.0592 divided by the number of electron transferred for this reaction, log ox على red. So we're doing the reduction potentials of the two half reactions separately. At equilibrium, when there's a mixture and there's any mixture, at equilibrium, eventually E of the reaction becomes 0. So whatever E red will be equal, E oxidation will equal E reduction. And so all I have to really do is find, so E red equals E oxidation half, or E cathode equals E at the anode, equals, we call it E of the solution. And if I find either E of the cathode or E at the anode, خلاص بكون أنا جبت ال E of the indicator electrode, because the E of the solution is our indicator electrode. And لأنه reference electrode is the She electrode, خلاص ال E of the solution is also the E of this titration at the end of the reaction. When the two reactants are mixed in stoichiometric proportion, it is said that the system has reached the equivalence of the titration. That is to say that the quantity of electrons that the oxidant can gain is then equal to the number of electrons that the reductant has lost. The amount of titrant that then introduces introduced makes it possible to determine the quantity initial present and the reactant to be measured. The equivalence can be detected either by a color change or by using a redox indicator or graphically. So there's also indicators that are changing color, مثل acid base, and we're going to look at some of them. Okay, let's look at the shape of the curve. So if I have reductant at the beginning and at the analyte, and the oxidant is my titrant. If I look at here, if I'm adding oxidant, what does that mean? It means that overall the E will be increasing because the E of the oxidant is usually greater than the E of the reductant. And E of the reductant is never zero, it's some point. So even if I have nothing, no oxidant added, مثل acid base, I already have a starting pH, and here I have a starting amount, and it's usually E naught of the reductant is the initial value. And we're going to see why, because I have no oxidant present, so the log value is 0. As I add more oxidant, the volume of oxidant being added, we're going to increase until we reach volume at equivalence, where the number of electrons exchanged is equal to each other, and we get E at equilibrium here and E at equivalence point. As well, we then add more oxidant, and here we have further oxidant being added, and the oxidant is the major species in the solution. Before the equivalence, the reductant is the major species in my solution. So reductant in excess, at equivalence point here, the oxidant is in excess. We're just looking at the shape of the curves now. If now my oxidant is my analyte and the reductant is my titrant. Okay, يعني الأوكس هو in the solution and I'm adding reductant. So the volume of reductant being added is on the X. Here, the oxidant always has a higher E, and when we're adding reductant, we're going to decrease the overall potential of the solution until we reach equivalence point, and then further reduction where the reductant becomes in excess. So at the beginning here we have, في غلط هون reductant in excess. هون on the top the oxidant is in excess and the reductant okay, what's here? We have more oxidant. So we have at the beginning the oxidant is in excess, and at the end the reductant is in excess. Yes, clearly. Okay, and so colors of the graph. Okay, so here my oxidant, I have more oxidant لأنه ما عم زيد reductant كتير. Just like acid base, if I start with an acid, let's look at this. The reductant on the bottom is like starting with an acid and I'm adding a base. The acid is in excess until I reach equivalence point, then the base starts to be in excess. In here, if I start with a base, okay, the pH will be high, and then I'm adding more acid, the pH decreases. That's like this value. Okay, now let's start an example of a titration, and And we're going to see relative to a reference She or chamomile electrode. Okay, so here we have a titration between selenium and iron, where my iron 2 plus is my analyte. It's in the solution. It's in perchlorate, which is a strong acid. And I'm adding from the burette as the titrant the Ce4 plus. Okay. In general, titrations, guys, always goes to completion. يعني نحن we choose the E naught values to be greater than 0.25 for sure. Delta E's of both E naughts, and always the K of the reaction for any titration is always chosen so that it is definitely complete reaction. Notice what they have done here to this one container titration. They have put the iron, in this case, they put a platinum plate, okay? And they put also a reference, which in this case, it's a, sorry, honey, the platinum plate. Only they put a reference electrode, which is the chamomile electrode, not the She, they put the chamomile, standard chamomile electrode. And the magnetic part. So the E of the solution will go on the cathode side because this is the platinum. They put him on the cathode. So overall E will be this E of the standard chamomile electrode minus the E of the solution, which is on the anode side. Clear? Okay. For us, again, we're only going to assume that we have to find the E of the solution for a titration. بس هي الأصل هيك. Okay. The half reactions, we have two half reactions. Fe3 plus goes to Fe2 plus 1 electron. This is the reduction half reaction, E naught. Ce4 plus goes to Ce3 plus in the reduction reaction. And so here both written as reductions, مع إنه ال Fe is actually undergoing the oxidation. It's going from Fe2 plus to Fe3 plus. So these are the reactions that are going to be taking place at the platinum electrode in form of electrode. Let's look at the two reactions. So what do we have on the bottom? What's the shape of the overall curve? We're going to see if I start with a reductant or an oxidant. So Fe2 plus goes to Fe3 plus 1 electron. The Ce goes to Ce2 plus. And it is then the Ce is undergoing reduction as the half reaction. So this is the oxidant, and this is my reducing agent, the Fe. And so if we have Fe2 plus in my solution at the beginning, and I'm adding Ce, we're going to start with a low E naught and low E, and we're going to start to increase. The easier is definitely to put the She electrode on the oxidation half and to put everything else on the reduction half on the cathode. So we're putting the platinum on the cathode and we're putting the She electrode on the anode. The harder is when I use a reference electrode, which is not the She electrode. Because in this way, خلاص ال E of the solution is your simple is your E. هلا في شغلة بس هون ما بعرف ليه قلتها هيك، خليني بس ارجع لها للصوت. This is the anode, this is the cathode, okay? So it's actually E of the solution. The E overall is the E of the solution minus E of the reference, which is the standard chamomile electrode. But if this was the She electrode, خلاص هيدا zero, so E is simply the E of the solution. For any redox reaction, the delta E naught is always E naught reduction minus E naught of the oxidation half. Okay, so the oxidant, the reduction reaction, يعني the oxidant minus the E of the reductant. فيكم تفكروا فيها بتسمي couples. So E of the selenium minus the E naught of the Fe, and we got it 0.94. We go ahead, let's find the K. Log K is N delta E naught divided by 0.592. We have the delta E naught. The number of electron transferred is 1, and we could see that this reaction is complete. 10 to the 15.8. We can find the equivalence point with a redox indicator or via an electrical measurement, such as the potential of the solution. We're going to see how we find the equivalence point from the potential of the solution. Whenever we have a mixture, we already said this, that at equilibrium, if it's in a one pot, E reduction will equal E oxidation. We call this E of the system or E of the solution. If I also have an indicator in a colored indicator in there, or some other oxidant and reductant taking place, all of the E's will eventually become E of the system. So the mixture is E of system or E of the solution. Let's look at this titration. Here we have this VE, the volume of selenium 4+, and we're going to read the potential. Let's look at it at each volume of added VE. When V of the selenium is 0, V2, يعني. This in terms of مثل الacid base, by the way, V is V added, V2, whatever we're adding, على V at equivalence point is the X. Okay, so we can write it in terms of the progress of the reaction X, which is the V added divided by V equivalence. So in this case, X is 0. So this is before the titration actually begins. And so we're looking at whatever the initial potential is. Who do I have at the initial state? I only have iron. Okay, I only have iron 2+ ions. There is no Ce4+. In reality, the solution contains traces of iron 3+, resulting from the slow oxidation of the Fe2+ by oxygen dissolved in the solution. So sometimes we see a little bit of Fe3+, but this amount is undetermined. I don't know how much it is, and we do not have enough information to apply the Nernst equation and to get an actual value. This redox potential is measured experimentally using a voltmeter and not calculated. And so this initial point, I can never really get it because I only have Fe2+ in solution. I don't have the other ion to be able to get E, let's say, of the cathode or E of the anode. Voltage can never be lower than the value needed to reduce the solvent. Since the solvent is water, and the value of reduction of water to hydrogen and two OHs is minus 0.828, this value here can never be below minus 0.828. Okay. But we can never calculate it. So unlike acid base, I can never get this. This value is only experimental. Yani when you do it and you do the reading, you read the potential. But this is the potential versus SCE, يعني مش versus the She electrode. So values will be slightly different than if I was looking at the She electrode. Okay. Now we're going to look in between. I haven't reached equivalence point, so I'm in this area. بالacid base كنا نسميها the buffer region. And in this values, we have still Fe2 plus is in excess, is greater than the Ce3 plus that's being added. So if I go to the equation, Ce4 plus, we can see, let's just directly go to the equation. You could do the reading on your own. The amount of Ce4 plus will be C2V2, and we're going to use a mole chart in this case. Fe will be C1V1. And since Fe is in the excess, يعني this Ce will tend to 0, and it will be the limiting reactant. So we're going to have some leftover Fe2 plus and some created Ce3 plus and Fe3 plus. Again, we want to calculate the E of the solution. The E of the solution, remember, EOX equal the E red equal the E of solution. I could use either the selenium couple or the iron couple to get the E of the solution. And typically, we always use the couple that I have already in my solution. So I will use the iron, whoever's in excess. So I will use the iron couple, find the reduction potential of the iron, even if it undergoes oxidation. So I will find the reduction potential, and I will say that that is my E of the solution. Okay, so E of the solution is the same as E of the Fe2 plus Fe3 plus couple, which is the E node of the couple, Fe, minus 0.0592 log of product على reactant or reductant على oxidant, red على odd, or plus. And here I use, because it's a ratio, guys, I could also use the simple moles. I don't have to get the concentration. So we end up getting C1V1 minus C2V2 على V total, C2V2 على V total. So the V total cancels. And that's it. Okay, so we use the E of the solution of the leftover species, which is the iron. Okay, that will be the E of the solution, E of the system, or E plus, because it happens to be on the cathode side. If we want to see the truth relative to a reference electrode, نحن بنجيب ال E of the mixture or the indicator electrode اللي هي ال E للiron, but then we must subtract, because this is on the cathode side, we will subtract the E of the reference. So if it is SCE, it's the E of SCE in a minus 0.245. We must subtract this number, and you can subtract him from the direct E node of iron. So بيطلع net إنه الcurve goes down. When I subtract SCE, the curve يعني the curve أنا اللي كنت عليه يعني لازم تكون هيدا you're taking this number and it's becoming lower. So the E is coming lower. The E that we find, E of the solution, is a little bit higher, and higher by a specific number, which is the standard reference electrode. For this course, we never have to do this. So you just simply say the E is the E of the iron الأساسي. Okay. Clear? So we never ever have to, subtract the reference electrode. Are we clear on this? At half equivalence, this is a nice point. At half equivalence, we will see that if I go back here to the chart, and if this number of moles is half the amount of C1V1, so C2V2, pick it all C1V1 divided by 2, half the amount. So this will become C1 divided by 2. So this will be simply C1 V1 times 2. So it will be like that. And ضربة 2 so 2. Okay. So half C1 V1. That's what we're left with. This will be كمان C1 V1 divided by 2 and C1 V1 divided by 2. If this was half the amount, C1 V1 divided by 2 originally, it will be net 0. We will see that the amount of iron at half equivalence, the species iron 2 plus equals iron 3 plus. And so at half equivalence, if we go back to the equation of the E at the cathode, it's E naught of the iron species minus 0.0592. Iron 2 plus equals the iron 3 plus. That means this is 1. That means all this term is gone. So E at the cathode simply equals what? L E naught of the Fe. And this is like the pKa at half equivalence with titration. El pH equals lel pKa of the acid in terms of acid. Okay. After equivalence point. After equivalence, now the Ce4 plus has been added to react all the Fe. No, this is sorry, at equivalence. There's equal amounts. Ce4 plus has been added to react with the Fe2 plus. So we have equal concentrations or number of moles. And in this case, so إذا أنا عندي C1V1 وهون C2V2 and they're equal to each other, that means this is going to be 0, this will be 0. This concentration I can either choose C1V1 or C2V2. Okay. Let's say like that. And now if you look at it, I don't have either electrode, yani I have nothing in excess. I don't have any Fe2 plus in excess. I don't have any Ce4 plus in excess. So I don't have a particular couple. Okay. So both reactions are in equilibrium at the platinum electrode. And I can supposedly use either the selenium or the iron species to determine the E at the cathode. Okay. But I don't have the Fe2 plus, I don't have the Ce4 plus. So I don't have this, I don't have that. So it's not easy for me to determine what are these. And that's how what they did is they added both potentials. And you're going to see this is when we add the two, because they're supposedly the same, right? Or E of the, eventually E of the solution, because we've reached equilibrium. So we add the two. Let's look at them. Add this, add that. And here it happens to be that this is 1 electron, 1 electron. We're going to see later that if it's more, then we have to multiply this مثلا N1 by the E first. But let's do this now. This happens to be 1 electron, 1 electron. Add the two equations. We get the E naught of the iron, the E naught of the Ce, minus 0.0592 log of this couple, minus 0.0592 log of this couple. Take the minus 0.592 and the log values out, and with a negative sign, that means the iron 2 plus Ce still remain on top. Iron 3 plus Fe4 plus remains on the bottom. Okay, so what happens to the log terms? If we are at equivalence point, we already said that the Ce3 plus will equal the Fe3 plus, and the Fe2 plus equals the Ce4 plus. So this term becomes log of 1. And since log of 1 is 0, that means simply 2E at the cathode equals the E naught of the first couple plus E naught of the second couple. So you take the E naughts, divide them by 2, and you are done. That's it. You get the E at the positive or at the cathode. The true cell voltage, in real, we have to subtract the chamomile electrode because E at the cathode minus the chamomile electrode, E at the anode, we get the true cell voltage. بس نحنا ما assume that the E is the she electrode always, and so it's 0. So خلاص, E at the cathode is simply your E for the complete reaction with the titration. After equivalence, now the CE is in XX. So C2V2 is greater than C1V1. The Fe will tend to 0, and your Ce is now the excess reagent. We subtract C1V1. This is C1V1, the limiting reactant. And now the couple that I have in solution, and I have its concentration, is the Ce couple. And so I will use the reduction potential of the Ce couple to get the reduction potential at the cathode. Minus 0.17 minus 0.592 log Ce3 plus Al4 plus, or plus. Solve, and so it's Ce3 plus red على ox C1V1 على C2V2 minus C1V1. Okay, again, do the chart. You're not going to sit there, memorize these. And then that's it. You get that the E is simply can be calculated from any C2 couple. When I have that the amount of Ce is 2 times greater, يعني at 2V equivalence. So here we have at V equivalence. A specific value point at 2V equivalence. So إذا هي 50 يعني على 100 بدي أطلع لل 100. Same volume. Okay. So if V equivalence is at 50 milliliter, 2V at equivalence is at 100 milliliter. That means that I have twice the amount of Ce than Fe. Okay, so if I have only 2 C1V1, Fe is 0, becomes 0. It's still your limiting. At equilibrium هو حيصير 0, هي حتصير minus C1V1, هي حتصير C1V1, وهون حيكون C1V1. So we can see that the Ce concentrations will be the same at 2V at equivalence. And this means that the E at the cathode is simply equal to E naught less Ce couple. So that's another value point that is interesting. So at half equivalence and at 2V at equivalence, we can get the E naught 1.171, the E naught of the Ce couple. While at half equivalence, we get the E naught of the Fe couple. Okay. Again, the real potential is always, we take the indicator electrode at the cathode, which is the E of the solution, and we subtract from it the reference electrode, which happens in this case to be the chamomile electrode. This is the real potential that is read on a potentiometer eventually. Okay, you don't eventually really read, you know, these values. You must subtract the reference electron. Okay. Now, for at equivalence point, there is an equation which is derived, which you guys should know because you're responsible for E at equivalence. Because we didn't calculate it yet. We just simply said that at equivalence point, we can't use neither the CE nor the FE couple because they're both equal 0, one of the species. So one of the ways that was done is indeed to add the two E's of the reduction potentials of the two species present. And when we add them, we also consider هون بس هاي الفرق هون كان عندي 1 electron هون عندنا مثلا لأول couple عندنا Na لتاني couple إذا عندي Nb, 2 different electrons. What I have to do first is I multiply the number of electrons by the top and bottom. يعني بيجي بحط Na على Na. Okay, because if I'm multiplying by 1, okay. So what happens is this Na goes away. So we're multiplying كل شيء by Na, standardized. So Na هون بتصير Na. هاي كمان بيصير عندي Na قبلها. Plus هون the Na actually is removed. And here we must multiply by Nb and this by Nb. When we multiply this by Nb, the Nb is removed. Okay, so we multiply everything by the number of electrons transferred. Add the two equations, you get طلعوا فيها. Add this part مع this part, the two reduction potentials. You get NaEA plus NbEB equals NaE naught A plus NbE naught B plus 0.0592 log of the oxidants على reductants, because there's a plus sign here, so that's good. Oxidants على reductants. However, at equivalence, we have A reductant equals B of the oxidant, and B reductant equals A of the oxidant. So this log value eventually becomes log of 1. So this log value is cancelled, and then you can solve here. And E of the A and E of the B سميناهن E of the solution. بس خليني أحطها E solution. E solution. Factor out E solution لبرا شو بتطلع؟ E solution ضرب Na plus Nb equals this value. So the E of the solution is the E at equivalence point in this case. E at equivalence equals Na E naught A plus Nb E naught B على Na plus Nb. وكل اللي عملته هلا I want you to memorize this equation that for any number of electron transferred, it doesn't matter what they are, but for simple redox reactions, for whatever number of electron transferred, one or more, E at equivalence point is أنا هحطها بطريقة تانية هون N1 E naught of the first couple plus N2 E naught of the second couple, and notice this is the number of electron transferred of that particular couple, divided by number of electron transferred of the first plus number of electron transferred of the second. So E1 E naught 1 plus E2 E naught 2 على N1 plus N2. And so if we look at this CE, FE at E of the system or E at equivalence, where at equivalence point, again, at all points, E of FE equals E of CE, but at this particular point, we have N للFE E node للFE couple plus N للCE E node للCE divided by N للFE plus N للCE. بسائب إنه number of electron transferred is 1 for either reduction half reaction. So 1 times E naught plus 1 times E naught plus 1 is 2. Okay, take the E naughts, divide them by 2 in this case, and you get the E at equivalence point. And so we already have, if I look at half equivalence, I get E naught reductant. 2 equivalence, I get E naught oxidant. At equivalence point, I can easily calculate because I get it from the E naught values. N1 E naught plus N2 E naught to N1 plus N2. This is the E at equivalence. And so I already have 3 value points before even starting the titration that I can put on a chart or I could use. Okay. Okay. The next example, I want you to go through it. هي نفسها اللي بعدنا already عملناها, but خلص بيحكوا عن E of the system directly, before and after. And so read it up. Let's see here. These are in terms of X. Remember بالbuffer at buffer. كمان we have terms in terms of X values لأن بالفنار بيستعملوا X ما بيستعملوا volumes and equivalence. We can divide the top and bottom by C1 V1 of any type and we get the values in terms of X. I don't see that there's any, preference of solving it in terms of X, but there are equations. والمشكلة بالX إنه ما بياخدوا into account the number of electron transferred, so it's a little bit different. Okay, so we're done with titration. We're going to do another example later after we start already the stop, yes. So pretty much the course eventually is done. هلا عملنا 1-to-1 titration يعني كان CE وقبلها 1. في فرق بس إذا بيكون ما عنا 1-to-1 and we will see that after we solve. منا big deal بس مثل هون FE مع 10 and I will go through this next example next time. But what I want to solve is first a few examples ونخلص قد ما فينا شو اسمه بالتداء, and then we also have at equivalence point with the added of a pH. ما في فرق actually بالcalculation بس إنه eventually I do want you to memorize a certain equation which is present here which is important. أسهل مش كل مرة بدكم تقعدوا تعملوا لها derivation. So just a few, a small part left in the course, which is a non-1-to-1 titration and the effect of pH coming. So this is called the asymmetric titration curve, which is when it's not 1-to-1. I will continue with that. مش next time, اللي بعدها. But for now, over the next lecture and on the weekend, we should be done with the TD كله تبع الcourse. So let me now with the TD you can, like I said, now you can solve pretty much everything with TD. Do you guys still recall what number we were at? Does anybody recall?
Finish number 12.
Finish number 12. Electrochemical batteries.